Good afternoon, my YouTube viewers. In this particular video, what we're going to talk about is the SARIMA model. And the SARIMA extends the ARIMA by incorporating seasonal components, making it ideal for data with strong seasonal effects. And so basically what we're going to do is we're going to write a program in Python and use the SARIMA model to forecast on the values. And in order for us to write the program, what we're going to need to do is to import 4 libraries in order to write the program. So the first library that we're going to import is NumPy as NP, which is a numeric library. And then we're going to import Pandas as PD, which is a data processing library, and it also creates data frames. And then we're going to import matplotlib.pyplot as PLT, which is a visualization library. And then from statsmodels.tsa, statespace.sarimax, we're going to import Sarimax. And from statsmodels.tsa.seasonal, we're going to import seasonal decompose. So statsmodels is Python's statistical library. TSA is the time series analysis module within statsmodels. And statespace is another module, and Sarimax has the Sarimax function in it. And seasonal is a model within time series analysis, and the seasonal decompose is a function in that too. So what we're going to do is we're going to generate synthetic monthly energy consumption data over a period of 3 years. And before we do that, what we want to do is we want to set our seed. And the reason why we set the seed is so every time we run the program, it will initialize to the same values. And you set your seed by typing np.random.seed brackets 42. Now we define our months equals pd.daterange bracket start equals 2020-01, comma, periods equals 36, comma, frequency equals ME. And then we're going to incorporate a trend equals np.linespace brackets 50, comma, 200, comma, len months. So that's going to be 36. And that's your linear growth trend. And your seasonality equals 30 times np.sign brackets 2 times np.pi times month.month divided by 12. So again, that's going to be 12. 36 divided by 12 is 3. And so that's your seasonal pattern. And noise equals np.random.normal. So that's a normal distribution. Brackets 0, 10, len months, that's 36. So that injects random noise into the signal. And energy consumption equals trend plus seasonality plus noise. And now we're going to create a data frame for the energy data consumption. Energy df equals pd.dataframe brackets, squiggly brackets, month, colon, months, comma, energy consumption, colon, energy consumption. So that means the first column is months and the second column is energy consumption. And so energy df.set index brackets month, comma, in place equals true. So what that means is the month has become the index and the energy consumption has become the first column. So now we're going to do seasonal decomposition to visualize the components. So result equals seasonal decompose brackets energy GF square brackets energy consumption, comma, model equals additive, comma, period equals 12, and then result dot plot, and then we're going to show it. So now we're going to split the data into training and validating sets, or training and test sets. train data equals energy df dot ILOC square brackets colon neg 12 square brackets, and you're going to use the first 24 months for training. Test data equals energy df dot ILOC square brackets neg 12 colon square brackets, and you're going to use the last 12 months for testing. So we're going to fit the SARIMA model. SARIMA model equals SARIMAX brackets train data square brackets energy consumption comma order equals 1 comma 1 comma 1 seasonal order equals 1 comma 1 comma 12 enforced stationarity equals false, enforced invertibility equals false, and SARIMA fit equals SARIMA model dot fit brackets. So you're going to forecast for the next 12 months. Forecast equals SARIMA fit dot forecast brackets steps equals 12. Forecast index equals test data dot index. So this is, you're going to use the test sets index for plotting. So you're going to plot the actual forecasted data. So PLT dot figure brackets fig size equals 6 comma 4 brackets PLT dot plot brackets energy df dot index comma energy df square brackets energy consumption square brackets comma label equals observed comma color equals blue PLT dot plot brackets forecast index comma forecast comma label equals forecasted comma color equals orange comma line style equals dash, and then we're going to put a vertical line in there. So PLT dot AXB line brackets x equals train data dot index square brackets -1 square brackets comma color equals gray comma line style equals dash comma label equals train test split. Now we add labels, title, and a legend to the graph. PLT dot title SARIMA model forecasting monthly energy consumption. X label is date, Y label is energy consumption. You get a legend and then you get a grid, and we're going to show the chart. So the first thing you've got is you've got your seasonal decompose, which we covered a seasonal decompose a few videos ago. So you may remember the seasonal decompose that we did a few videos ago. So you've got your energy consumption for a period of 36 months. You've got your trend for a period of 36 months. You've got your seasonal for a period of 36 months. And then you've got noise. I think that's a noise. Residual, for a period of 36 months, 24 months or 36 months. And then now we've got the SARIMA model. So forecasting monthly energy consumption. So the observed values are in the blue line, so you can see the observed values. The forecasted values are in the orange line, and the train test splits it between the first 24 months and then the last 12 months. So that's it. That's a good SARIMA model, and that's how you do it. But what you're going to do is you need to know how to calculate the PDQs. And so this is the code to calculate a PDQ in the SARIMA model. And basically what I've done is I have hashed everything out, but to make it a comment. But when you want to use it, you have to take out the comments and make it active. And so what I've done is I'm just leaving it there so you can either pause your video and copy it if you want to pause your video. And then so that gives you the SARIMA model to calibrate your PDQs. Because you'll notice here, if we go back to where it says the SARIMA models, okay, it says order equals 111 and seasonal order equals 11112. So what you would have to do is you'd have to calibrate your PDQ and then get the best fit and put the best fit in the order. So it might not necessarily be 111, but that's what we've got. And the seasonal order might not necessarily be 1112. It might be 12112 or something like that. But so the SARIMA model is more complex than the ARIMA, because the SARIMA model has a seasonal component into it, which the ARIMA model doesn't. So you're probably, if you want to use the SARIMA model and you want to calibrate the PDQs, it's probably going to take a lot of trial and effort, a lot of practice to get it done correctly. But that's why I did actually give you the code to calibrate the PDQ if you want it. But I will say, because this course is just a course on statistics, so I probably am going to make a course just on time series analysis with Python, and then that will go in more in depth into the different models that they have. But I just wanted to show this to you. So this concludes our video, and the next video we're going to talk about another time series analysis topic, and I hope that you decide to watch it.